We're just going to look at some results that arise out of our different polynomial theorems and what have you. So the first idea is this. If we know a polynomial and we've found k of the zeros, then we know that each one of those will create a linear factor. And so therefore, when I multiply all those linear factors together, whatever that happens to equal must be a factor of the polynomial. So that's all it's really saying. We've got this quartic, and we know that 1 and negative 2 are zeros. We now have to factorise it. Well, oh sorry, I misread it. We have to show 1 and negative 2 are zeros. So use our factor theorem, polynomial 1, yes indeed, that turns out to be 0. Polynomial negative 2, that turns out to be 0 as well. So yes, we now know x minus 1, x plus 2 is indeed a factor. So we want to factorise it. But notice I didn't write down the factor x minus 1, x plus 2. It made more sense to expand it out. So then I can just look at it and solve it by logic. Again, using the idea of leading term times leading term. So we get x squared, constant times constant, plus 5. Now, is there a missing term? At this stage, if we were to expand this out, we'd get 5x. Oh, that's all we want. Okay. Oh, not comfortable. I might double check. Let's have a look at the x squareds. What would we get with the x squareds? I'd get 5x squared minus 2x squared. 3. Oh, no, okay. Seems to be all right. So the other factor is just x squared plus 5. That, of course, doesn't factorise. Well, not using real numbers anyway. So we'll end up with x minus 1, x plus 2, x squared plus 5. Okay. So the second idea. Say we know the polynomials of degree n, and we've actually identified n zeros. Well, then we should be able to factorise it completely. That's assuming it's monic. Now, if it wasn't monic, I'd have a constant out the front, of course, and that would fix that up. You cannot have more than n zeros. So whatever the degree of polynomial is, you can't have more. Quadratic, maximum of 2. Cubic, maximum of 3. So on and so on. So using that idea, we have a polynomial. What do we know about it? We know it has a double zero at negative 7. So x plus 7 squared would be a factor. Single zero at 2. X minus 2 is a factor. So write down a possible polynomial. And when I mean a possible polynomial here, what I mean is a general one that will cover every possible situation. So we know there'll be a factor x minus 2, x plus 7 squared. Now, we're just saying a polynomial, so it could be degree anything. So I would multiply it by, well, I'm calling it qx. But there's some conditions on qx. Qx can't have a 0 at 2 or negative 7. Because if it did, then we'd no longer have a single 0 at 2. I'd have a double 0 at 2. Or if it was negative 7, I'd have a triple 0. So I need to specify I can't have those ones. Whether I need this next bit or not, it probably doesn't matter, but I just put it there. Because of course it could be any multiple. But do I need that? I guess I don't have to have it, because that multiple could be inside the polynomial qx itself. But, all right, I'll just multiply by k to say, look, I could have any multiple of this. We restrict it a bit more. Monic polynomial, degree 3. Again, we already know those factors, and that's where I'm going to stop, because that's degree 3. So it can't have another factor, and it's monic. So that's it. There's only the one possibility there. What if it was of degree 4? Okay, so again, we have those. There must be one other factor. It's got to be a linear factor to get it to degree 4. So I'll call it x minus a. A can't be 2 or negative 7. In this case, I will need... Oh, no, it said monic. I was going to put a k there, but no. It has to have a coefficient of 1 on the highest power, so there's no constant out the front. So a polynomial of degree 5. Okay, it's cubic at this stage, so I'll multiply it by a quadratic. Now, I haven't written it down as a quadratic. I've simply said qx is a polynomial of degree 2. And again, I need to specify I can't have a 0 at 2 or negative 7. I'm going to multiply by k because it didn't say it was monic. But again, do I really need that? That k could have been in the qx itself. So you get away without the k. And now, number 4 is where I now contradict myself. Because remember, number 3, I said it can't have more than the degree. So, point 4 here says, well, if it does have more than n, which I just said it can't, but if it does, then our polynomial is a very specific polynomial called the 0 polynomial. It's a very weird polynomial. 0 is just a really weird number, because polynomial x equals 0. It satisfies the rules, or does it, for a polynomial. Like, is that a polynomial? What were our rules for polynomials? Okay, but x to the power of 0, that's an integer power, satisfies that rule. What were some of the other rules we said? No, we did say 0 was okay, because remember, if it was polynomial equals, I think 7 was the one we used, that was a polynomial. So, what's the story with 0? There's another little proviso I put in there where we said, well, put it this way. What's the degree of this polynomial? Is it?
It's anything, because the constant in front is 0, so anything.
Yeah, could be anything. Say some people would say, is it a polynomial at all? Because there was one little condition there. If you remember, we said the leading coefficient could not equal 0. Well, surely 0 is the leading coefficient in this polynomial. So, if you get this situation where they tell you, it's a lovely question if it does appear, it really searches out who knows their theory, I guess. They say, oh, I've got this cubic. It has solutions of, well, no, they won't say what the solutions are. They'd say it has maybe 4 solutions. What's the polynomial? No, it's got to be 0. It's the only thing that would satisfy all that. Why is it true? Because if you substitute any number into that polynomial, what do you get? 0. So it satisfies the factor theorem. So you got all that. It's 0. 0 is just weird. Okay? But it's like if we're just dealing with numbers, what are the factors of 0? You might not have ever thought of that. But what are the factors of 0? Everything. Because you can always go 0 times that. That's why we don't use 0 when we're doing factors, because it just mucks the whole thing up. It just weird number. Some people say it's not even a number. Right? It's just this symbol we use to represent the absence of value. I mean, we need it because it has to hold place value in numbers and things like that. But is it really a number? Anyway, enough philosophy there. Okay. Now, number 5. If you've got 2 polynomials and they are identically equal. So notice I have the congruent symbol there, not the equal symbol. Right? So it's not a mistake. I mean to put it there. What we're saying is, it's not that these polynomials are equal. We're saying they are the same polynomial. It's like when you have congruent triangles. These triangles are the same triangle. So these polynomials are the same. Now, if that's true, then the coefficients of every term must be the same. So the constant must equal the constant. The coefficient of x must equal the coefficient of x. And so on and so on. So in this one, A1 must equal A2, B2 must equal B1, C1 must equal C2, and so on and so on and so on, because they are the same polynomial. Let's play with 10e.